Welcome to Technical Sales and Consulting's Training to Go e-learning series. This module will cover electrical test equipment and insulation theory. It is dedicated to technical expert Dave Rosenfield. It is designed to provide product knowledge for all levels, from beginner to expert. At the conclusion of this module, you can register to receive your certificate of completion. Be sure to take advantage of this opportunity to use this documentation as proof for your technical certification requirements or continuing education credit. Now let's get started. This is the outline for what will be covered in this module. First, we will establish some knowledge of fundamentals and basics that will help guide us through the lesson. Along the way, we'll emphasize some definitions that will be useful in understanding test equipment. Many tests of electrical equipment involve insulation integrity, so we'll spend some time examining properties of insulating material. We'll look at some test equipment. We will also examine an overview of equipment as well as how they are used to perform tests. We will then summarize the lesson. Before we get too deep into our lesson, let's take some time to go over some fundamentals that will help us as we progress. Now, what are we measuring with electrical test equipment? Voltage is one of the parameters. It can be DC or direct current, or AC, or alternating current. Current is also a value helpful in evaluating electrical equipment. It can also be DC or AC. Nearly most electrical equipment have some sort of coil in them. That is why resistant values are needed to determine the health of a component or an assembly. Lastly, with the reference of a wiring diagram, continuity becomes important for troubleshooting equipment. More on these as we build our knowledge of test equipment. NFPA 70E refers to IEC standard 61010 that defines test tool category rating. This table shows these categories with their description and uses. Category 2 covers single-phase receptacles and connected load. Typical applications are household appliances, power tools, outlets more than 30 feet from a Cat 3 source, and outlets more than 60 feet from a Cat 4 source. Category 3 covers three-phase circuits and single-phase lighting circuits in commercial building. Applications are equipment in fixed installations such as three-phase motors, switchgear, and distribution panels, lighting circuits in commercial buildings, feeder lines in industrial plants, and any device or branch circuit that is close to a Cat 3 source. And finally, Category 4 covers connection point to utility power and outdoor conductors. Applications are primary distribution panels, overhead or underground lines to detached buildings, incoming service entrance from utilities, and outdoor pumps. Instrument manufacturers place this rating in their literature and on the device. Make sure you're using the proper rating for the application. When measuring current, the Fluke clamp-on meter is the instrument of choice. The device allows the technician to open a clamp and wrap it around the cable to be measured, as seen in this photo. This acts much like a current transformer, sensing the current traveling through the conductor and registers the reading on the display. If we zoom in on the dial, we can see all the functions this meter performs. First is a symbol for amps or current. When in this mode, the unit will sense the current from the cable clamp. The other dial positions will need to have probes seen here connected. Here you see the symbol for ohms. This allows you to do a continuity check. Next you see the symbol for DC direct current voltage. And lastly is the symbol for AC alternating current voltage. This tool is extremely helpful in troubleshooting circuitry. This is a Hafele Tetex 2293 combination 3-phase winding resistance meter and transformer turns ratio tester. This unit performs both 3-phase winding resistance and turns ratio testing on a transformer without the need to switch cables. This picture shows a setup of the tester on the oil-filled transformer. Other sets are made by Raytec and Vanguard. When used to test the turns ratio of the transformer, the primary and secondary are hooked up, including the XO terminal. The primary is then ejected with voltage, and the secondary is measured to determine the ratio coming out. Current transformers are used to sense amperes on switchgear. They monitor high currents and reduce the signal down so that it can be read on an ammeter or as an input to a protective relay. The primary can be 8,000 amps or higher, and the secondary is always 5 amp. These need to be extremely accurate in order to provide proper protection of equipment. Therefore, they require testing. Now, what functions need to be tested on current transformers? Let's look at these parameters as viewed on a CT analyzer screen. A ratio test is performed. If the ratio is not consistent, accuracy to the meter or relay becomes inaccurate and could cause a catastrophic failure. The tester makes sure that the CT has the proper polarity also. The polarity of a current transformer is extremely important. It's just like a battery. A current transformer too has a polarity. The polarity determines the direction of the secondary current in relation to the primary current. Wrong connection of the current transformers can cause false operation of the protective relay. A resistance check is also performed. The burden or load on the CT is also determined. The test set also puts the CTs in phase angle accuracy, making the necessary connections. A saturation test is performed by applying an AC voltage to the CT secondary and increasing the voltage in steps until the CT is in its saturation. The test voltage is slowly decreased to 0 to demagnetize the CT. Other brands of testing devices are the CT2020, Megger, and Lithinix. These all have YouTube videos demonstrating the operation of the test set. The most common test instrument that is part of every electrician's toolbox is the multimeter. Today these all have digital displays, but back in the day the analog multimeters were used as seen here. Multimeters are used for first-level testing and troubleshooting. Let's take some time to examine it and see its capabilities. Let's start with a brief overview of this ideal multimeter. It is important to note that all multimeters have similar features. Here you see it in the off position. It includes a digital display, mode dial, connection jacks, and a set of probes. There are also two buttons labeled range and a button that allows you to toggle between AC and DC amps. More on these later. Before we start, we should take notice of the position of the probe plugs. The probes are color-coded to match the corresponding locations on the multimeter. For voltage, resistance, and continuity, the probes are positioned here. Later we'll move them for measuring current. Time to step through the selections available on the rotary selector switch. The first position is for reading DC voltage. You can see this position is labeled with a V and the symbol for DC. While in this position, you can select the range which you wish to measure. By tapping the range button, you can move the decimal point to thousands. If you tap it again, it will move to hundreds, and one more time it takes you to whole numbers. Tapping it again brings it back to thousands. Next, we can move the dial to AC volts position. Again, you see the letter V with the symbol for AC voltage. The same range settings are available by tapping the range button, thousands, hundredths, and whole numbers. Continuing to move the selector to the next stop, we find a symbol for ohms. This position is used to check resistance. For example, you might be checking the resistance of a starter coil. If you know the resistance rating of the coil, this position will provide the actual measurement to help determine if the coil is within spec. No doubt at some point you will need to check for continuity. In this next position, you will find a symbol for continuity. Also, right above it, you see the audio symbol. This is helpful by giving an audible beep to indicate total continuity. This can be toggled on and off by tapping the button seen here. Now we move to the current settings. Small UA represents microamperes. While in this position, you can toggle the range from tenths to whole numbers. You must also tap the DC/AC button to select whether it's DC or AC current. One other thing you notice is that you might see the last place on the display float between 0 and 1. Cycling the AC/DC button usually will reset this back to 0. It is important to note that the red probe must be changed to the UA/MA position to get the proper reading. The next position is milliamperes. This time the range can be set for hundredths or tenths. You also need to tap the AC/DC button to determine if you're measuring DC or AC current. The last position is the 10 ampere position. This will allow you to check for amps up to 10. The range is either hundredths or tenths. When in this setting, the red probe must be moved to the 10A position seen here. Just as a review, the value 1 with 6 zeros after it represent microamperes, and that is equal to 1 amp. When you look at milliamperes, 1000 milliamperes represents 1 amp. 100 milliamperes represents 1/10 of an amp. 50 milliamperes is equal to 5/100ths of an amp. And the last example we'll cover is 20 milliamperes is equal to 2/100ths of an amp. You may want to consider adding alligator clip leads. This helps free up your hands when getting a measurement. These are available with the leads seen here, or ones that can attach to a standard probe. Another feature to free up your hands are spring clip leads. We must emphasize at this point that extreme caution needs to be maintained around electrical circuits and when using a multimeter. Here is a short video demonstrating using the multimeter to check the continuity of a fuse. Notice that the display shows a reading of 0, indicating that the fuse is good and can still be used. For any technician to have is a non-contact voltage tester. Making certain that the test specimen is de-energized is essential to a safe and successful test. Here is a non-contact voltage sensor made by Southwire. There are a number of manufacturers that make the same device. They range in price from $9 to $30. This can be used from 100 to 600 volts. It quickly checks for the presence of live voltage on outlets, wiring, circuit breakers, lighting fixtures, and switches. It provides a visible and audible alarm to indicate the voltage is live. Here is a quick video demonstrating the use of this tool. This is Southwire Tools model 40116N non-contact voltage detector. It is rated 100 to 600 volts AC. As you can see, it is a pen style so that it can be placed in a pocket and kept close by. It has a built-in flashlight. It provides a green LED display, which will turn red when it senses a live voltage. It also provides an audible signal when it senses a voltage. It carries a Cat 4 safety rating. And when selecting materials for insulating systems, all of the following need to be considered. They must have the ability to withstand electrical stresses, mechanical stresses, and thermal stresses. Insulation is a primary concern when testing electrical equipment. The more terms we become familiar with, the better we'll be prepared to understand electrical testing. Aside from the characteristics we previously discussed, insulation falls into specific classes starting at Class A through to Class H. Let's reflect on these. Class A covers a temperature range from 105 to 120 degrees C. Class B temperature range starts at 130 up to 155 degrees C. Class F is rated at 155 to 180 degrees C. And finally, Class H, usable temperature is 180 to 200 degrees C. Typically, Class A materials are organic such as cotton, silk, or paper. Class B and F tend to be more synthetic or inorganic materials such as mica, glass fibers, asbestos, and polyester foam. Class H utilizes inorganic materials such as silicone that could withstand the higher temperature rating. Some words of caution. When servicing equipment, never replace any insulating material with anything other than the original OEM materials unless approved by a certified professional engineer. Insulation plays a vital role in protecting equipment and personnel. Here you see a typical view of a cable. It consists of a conductor or multiple conductors with an external insulation jacket, usually made of PVC. The purpose of insulation is to protect any potential energy from escaping the envelope. If energy or voltage escapes, damage to equipment and injury to personnel could occur. Next, you will see the importance of testing insulation in an attempt to discover any compromise in its state. Before we go any further, let's talk about insulation a little more and look at some terminology that will help us understand testing and test equipment more easily. First off, every single electrical circuit uses insulation. The necessary properties of insulation are: it most importantly needs high resistance to the flow of electrical current. It also needs to be able to withstand electrical stresses, and it also needs to be able to conduct heat. We'll examine some more terminology in the next slides. There are some additional properties of insulation that are necessary and desirable. Resistance to surface leakage is one. As the illustration shows, current can creep along the edge of the insulation. Let's pause for a minute and define leakage current. Leakage current is the resistive current that flows through the insulation, and this is a value that is measured during an insulation resistance test. Obviously, a lower leakage current implies an insulation system in better condition. The leakage current should stay more or less over the test period. Moisture is a real concern and a problem with any electrical circuit, so resistance to moisture is a plus. Industrial environments may contain chemicals. The insulating material should be resistant to chemicals. Many electrical circuits are around machinery where oils and other contaminants are present. Insulation should be resistant to these. More electronic devices are being used today, so some concern should be considered for insulation that is resistant to RFI, or radio frequency interference. Mechanical properties are another consideration, such as vibration or other stresses. And lastly, temperature in the environment needs to be appraised when choosing insulation. You may have heard the term dielectric used. Let's look at the definition. Dielectric is a designation used to identify a medium or substance that transmits electric force without conduction. As used in the electrical industry, this is an insulator or insulation. The energy required to charge the dielectric is recoverable in whole or in part when the charge is removed. The term dielectric was coined by William Whewell from dia, D-I-A, and electric in response to a request from Michael Faraday. This is an illustration that might be helpful. Notice that the charge is applied here, positive on the top and negative on the bottom, and the dielectric material is shown here. Perfect insulator can be represented by an ideal capacitor as shown here. The electrical representation can also be seen. The perfect representation is shown with a 90-degree angle. However, all electrical equipment insulation has losses, and therefore an insulator is not a pure capacitor. Thus, the electrical circuit of a practical insulator can be represented by a capacitor with a small resistance in parallel with it, as seen in this image. Now, how does it work? Let's think of a water pipe with water flowing through it into a tank as seen here. The water will continue to flow until we shut off the valve. Then, no water can flow. Then the tank will store some of the water, but we continue to get water flowing out of the pipe. When we close the valve, water will stop pouring into the tank, but we'll still get a steady supply of water out of the tank as it empties. Once the tank is filled again, we can open and close the valve. As long as we do not completely empty the tank, we get uninterrupted supply of water out of the end of the pipe. So we can use a water tank to store water and smooth out interruptions in the supply. In electrical circuits, the capacitor acts as the water tank and stores energy. It can release the energy to smooth out interruptions to the supply. If we switch the simple circuit on and off very fast without a capacitor, then the light would flash. If we connect a capacitor into the circuit, then the light will remain on during the interruptions, at least for a short duration, because the capacitor is now discharging and powering the circuit. Capacitors come in many shapes and sizes and are used in a variety of circuits: power, control, and electronic. Many applications you see every day and do not give it a thought. They are used in ceiling fans, power factor correction for industrial plants, capacitor start motors, which you might find in HVAC applications, variable frequency drives, and many more. Long runs of cable also have potential to store energy even though the power is switched off. Therefore, extreme caution must be taken when testing and troubleshooting equipment with capacitors and cable runs because of the ability to store energy. Another important term that is helpful in understanding insulation principles is dielectric constant. Here's the definition. Dielectric constant is known as specific inductive capacitance, capacitivity, or permittivity. The dielectric constant of any medium or material is defined as the ratio of the capacitance of a given configuration of electrodes with the medium as a dielectric to the capacitance of the same configuration with a vacuum or air as the dielectric between the electrodes. The term in calculator is used to determine the effectiveness of a capacitor. The ratio is also referred to as permittivity of a substance to the permittivity of free space. Let's try to explain the concept another way. Dielectric constant is the ratio of the capacitance formed by two plates with a material between them to the capacitance of the same plates with air as the dielectric. Below are two illustrations that might make this clearer. The one on the left shows two plates with air or vacuum medium, while the right shows two plates with an insulation medium. No matter what the medium is, it's always compared to air or vacuum. The formula seen here can be used to determine the ratio. K for the dielectric constant is equal to C1, or capacitance 1, over C for capacitance of the electrodes with air or vacuum. Capacitance can be calculated by the following formula. C equals Ka divided by D, where A is the area between the electrodes, D is the thickness of the insulation or the spacing between the electrodes, K is the dielectric constant of the insulation or air. The dielectric constant of K of air is practically unity, and the dielectric constant of the other insulation materials is defined in terms of air or vacuum. Let's look at the table showing the dielectric constant values of other insulation materials. Vacuum and air, as we said before, have a value of 1. Paper is 2 to 2.6. Rubber is 2 to 3.5. Oil is 2.2. Bakelite is 4.5 to 5.5. Fiber is 2.5 to 5. Glass is 5.4 to 9.9. Mica and wood is 2.5 to 7.7. Porcelain is 5.7 to 6.8. And polyethylene is 2.3. We're going to continue examining terminology that will help us in discussing tests such as insulation resistance tests. Dielectric absorption is next up. Definition is, dielectric absorption is a phenomenon which occurs in dielectrics whereby positive and negative charges are separated to respective polarity when a DC voltage is applied to the dielectric. This phenomena is time-dependent and usually manifests itself as a gradually decreasing current with time after the DC application. Later you will see how this is used to determine a DAR, or dielectric absorption ratio, in an insulation resistance test. The next term to review is dielectric loss. Here's the definition. Dielectric loss is the time rate at which electric energy is transformed into heat in a dielectric when it's subjected to an electric field. Dielectric loss is measured in watts and is a measure of energy dissipation through and over the surface of the insulation. The dielectric losses of most insulations increase with increase in temperature, moisture, and corona. Insulations may fail due to the cumulative effort of temperature, that is, rise in temperature causes an increase in dielectric loss, which in turn results in a further rise in temperature. This phenomenon is self-perpetuating and continues until the insulation fails. Another term we will examine is dielectric strength. Here's the definition. The dielectric strength of a material is the potential gradient voltage at which a breakdown or electrical failure occurs and is a function of the material thickness and its electrical property. In other words, it is the maximum electric field which a capacitor can withstand without breaking down. When a complete breakdown occurs, the dielectric transforms into a conductor. Dielectric constant and dielectric strength sometimes get mixed up. Let's take a time out to review the features of both. First of all, the dielectric constant is the ability of an insulating material to store electrical energy, while the dielectric strength of an insulating material is its ability to act as an insulator. Dielectric constant is a quantity measuring the ability of the material to store electrical energy in an electrical field, while dielectric strength is a measure of the electrical integrity of an insulator. Finally, dielectric constant has no units or dimension. It is simply represented by the numbers or value. Dielectric strength is a unit of the electric strength and is defined as volts per meter, or V over M. Earlier, we looked at the important characteristics of insulating material. It is now time to look at the important electrical properties. First off is volume resistivity. Volume resistivity of insulating materials measures how strongly a material composition opposes the flow of electric current through a volume of cubic specimen. The lower the resistivity, the higher the conductivity, namely as the electric charges meet a weak resistance to circulation. Power factor is another concern. Just as a refresher, the formula for power factor is seen here. Let's reflect on the concept a little further by looking at the beer that made power factor famous. The entire mug represents the demand power required. The liquid portion is the useful power, while the foam represents the wasted power. Dissipation is the term used with power factor when considering insulating material. Dissipation factor is a measure of the dielectric losses in an electrical insulating composition when used in an alternating electric field of the energy dissipated as heat. A low dissipation factor or power factor indicates low AC dielectric losses. Capacitivity, as we saw earlier, is the ability of the insulation to hold the energy. Dielectric constant is another important characteristic, and we examined this concept previously. Different materials have different specific ratings. AC impedance is the ratio of voltage to current within alternating current. Impedance can be extended by the idea of the AC circuit resistance and include both phase and magnitude. The term is widely used when discussing transformers and helps determine efficiency. It is usually represented by the letter Z. Lastly, dielectric strength, as we discussed, also becomes important, mainly because you do not want the insulating material to break down and then become a conductor. A corona discharge is an electrical discharge caused by the ionization of a fluid such as air surrounding a conductor carrying a high voltage. It represents a local region where the air or other fluid has undergone electrical breakdown and become conductive, allowing charge to continuously leak off the conductor into the air. A corona or ionization occurs at locations where the strength of the electrical field around a conductor exceeds the dielectric strength of the air. It is often seen as a bluish glow in the air adjacent to pointed metal conductors carrying high voltages and emits a light by the same mechanism as a gas discharge lamp. The shape of the energized surface can affect the ionization. Smooth surfaces are less likely to produce ionization at a given voltage level. A great example of this is the discharge of a Tesla coil. Here is a photo of a Tesla coil at the Amalie Arena in Tampa, Florida. Quite a display when the Tampa Bay Lightning score a goal. Do you want a more spectacular presentation of corona? Here is a presentation of the operation of a Tesla coil, courtesy of Romac Industries. When ionization in the air occurs, one of the products is O3 or ozone. Ozone combined with the presence of moisture produces nitrous acid. The etchant effect of this, along with white oxidation, can be seen as residue on electrical equipment. Non-destructive testing, or NDT, as the name implies, refers to an array of inspection methods that allow inspectors to evaluate and collect data about material, system, or component without permanently altering it. All of the previous characteristics of insulation except dielectric strength can be assessed by non-destructive testing. These tests are AC dielectric loss, power factor or dissipation factor, capacitance, AC impedance, radio frequency interference, DC insulation resistance, and DC dielectric absorption. Before we look at different test equipment, it is good to keep in mind the differences in equipment voltages and test voltages. A quick review of this table will be helpful as we progress through the module. Equipment AC ratings up to 100 volts usually use a DC test voltage of 100 and 250 volts. AC equipment voltages of 440 to 550 volts are used with DC test voltages of 500 and 1000 volts. 2400 AC equipment voltages correspond to 1000 to 2500 volts or higher. 4160 AC volts or higher utilize 1000 to 5000 volts or higher. Now, how do we make sure that the integrity of the insulation has not been compromised? The testing method that gives the best result is a DC high-pot test. Now, just what is a DC high-pot test? Well, as the name implies, it is a high-potential test using DC or direct current. The DC voltage is introduced to the device and gradually increased during the test. Basically, it can be defined as a test to verify the integrity of the insulation between a circuit which was designed to protect the user. Technicians sometimes refer to this as testing the dielectric strength of a device. The device under test is referred to as DUT. The devices include any insulating device, but in particular electric motors and generators, transformers and switchgear, circuit breakers, and electric cables. High Voltage Incorporated makes a PTS series to perform this test task. These kits are portable and can easily be set up in the field as seen here testing cables and switchgear. There are AC high-pot testers available, and some manufacturers can provide dual AC and DC high-pot instruments. In the next visual, we'll look at the basic features of the tester. Hafele High-Potronics makes a digital version of this test set. Phoenix is also another popular maker of the DC high-pot test sets. To help familiarize you with the test kit, let's take a quick tour. First, there's the power on and off switch. Next, you see the high power on and off switches. Here is the ground clamp and load return clamp connection terminals. Now let's look at the meters. On the top is the voltage meter that displays the output voltage. The meter has two scales controlled by a range switch. The output voltage is increased in steps by using this output dial. The current meter registers any readings generated by the test. It too has two scales that are regulated by a current meter range switch. These are the basic features. Further video instructions, safety features, and connection information can be found on HVI's website, hvinc.com. Contact resistance testing is a common non-destructive test. First off, let's define the term contact resistance. Contact resistance is the resistance to current flow due to surface conditions and other causes when contacts are touching one another in the closed condition of the device. This can occur between contacts of circuit breakers, contactors, motor starters, relays, switches, or bus connections. The test is also referred to as ductor testing. Now, why is this test important? Measuring the contact resistance helps identify corrosion on the contact surfaces and allows contact corrosion to be diagnosed and prevented. The test can identify potential trouble spots such as loose connections, proper torque of bolted joints, and contact erosion. Increase in contact resistance can cause a high voltage drop in the system which needs to be controlled. Contact corrosion leads to power loss, heat generation, loss of contactor capacity, and failure to interrupt current when required. Let's spend a little more time on this subject. There are a number of devices that can be used for contact resistance testing. A micro-ohmmeter such as the AEMC 6240 shown here, a mega-ohmer like the AEMC 5050, a milliohmmeter similar to the Megger BT51, and lastly static resistance tester or DLRO, which stands for Digital Low Resistance Ohmmeter similar to the AE MC6250. This tester consists of a DC ammeter and a few other components. The test measures the resistance in micro or milliohm level. All use a 4-lead Kelvin method of testing. We'll explain the Kelvin method in an upcoming visual. Some of these types of meters are also available in handheld type. For demonstration purposes, we will focus on using the DLRO to accomplish this test. A DLRO, or digital low resistance ohm meter, is utilized to check the integrity of contacts of electrical switching equipment. Take for instance a circuit breaker. The surface contacts of this DS circuit breaker over time will form oxidation. Corrosion on the contacts is also a possibility. The normal operation from interrupting circuit loads could wear away the contacts. These conditions prevent proper power flow through the circuit breakers. Therefore, a resistance test is needed. The DLRO is used. Most testing procedures guide a technician on how to perform the test and analyze the results. Let's look at EERS 2018 taken from Pearl. Section 1200 covers circuit breakers including molded case, insulated case, and power breakers. Here is an excerpt from that section. Item 2.2 covers contact resistance. Continuing on, it reads 2.2.1, perform a contact resistance test using a digital low resistance ohm meter. The next step is 2.2.2, which is record results. Then 2.2.3 is compare test results to manufacturer's recommendations if available. Section 2.2.3.1 covers a Pearl-recognized method of comparing test results of each pole. Results should be within 50% of any of the poles. Any industry standard used shall provide at least the same integrity of each pole and ensure that they are within 50% of one another. It is important to note that these procedures can also apply to medium voltage breakers as well as contactors, starters, and medium voltage switches. Now let's look at the DLRO in some detail. The DLRO uses a Kelvin 4-wire test method. The source leads provide a constant current while the sense leads measure the voltage. This provides a high level of sensitivity and accuracy when the load under test is of low resistance. This clamp shows the P1 and C1 source and sense probes. This works well on flat surfaces, however it is a challenge when testing circuit breakers with finger cluster terminals. A Kelvin clamp seen here can be screwed into the stud after removing the cluster to provide test points for the probes from the DLRO. Now we can go over the instrument itself. Here is where we make the connection from the leads connected to the item being tested. Note that they are color-coded red and black to correspond with the leads. Also note that the leads are marked C1, P1, C2, and P2. Additionally, there is a pictorial graphic indicating the testing connection. Every manufacturer of micro-ohm meters usually has a set of function buttons to facilitate navigating display, printing results, and stepping through memorized results. This button initiates the test. The set can be set from 5 milliohms to 2500 ohms with an input current from 1 milliamp to 10 amps. As you step up the selector switch, you increase the sensitivity and move the decimal point on the display to get a more finite reading. Oftentimes this device is confused with a mega ohm meter. While both devices measure resistance, the DLRO is designed to detect very low levels of resistance. We will examine the mega ohm meter a little later in this course. Primary injection testing is the optimum standard for testing the performance and integrity of circuit breakers. Shown in this image is the ETI PI6000 primary circuit breaker test set. Let's start with a definition. A primary injection test set injects programmed multiples of the rated fault current of the breaker through the breaker while measuring the trip time. Primary injection testing should be in accordance with NEMA AB 4-2017 Guidelines for Inspection and Preventive Maintenance of Boulder Case Breakers used in commercial and industrial applications. There are 4 tests that need to be performed. Let's look at these tests and illustrate where they exist on a breaker trip curve. First is the long time delay and pickup. This is represented by the blue line seen here. This provides protection for overload conditions. The test current is injected in each pole and the trip time is recorded. Next is a short time delay and pickup, represented by the red line on the curve. This is an intentional preset delay to provide coordination with other protective devices. The test current is usually 1.5 to 2.5 times the short time pickup and is injected in each pole of the breaker, and the trip times are recorded. Typically, the results are in milliseconds. This is followed by an instantaneous pickup represented by the yellow line on the curve. This provides short circuit protection. In this test, current pulses are injected in each pole and then steadily incremented. The value of the pickup is recorded. The last test is ground fault delay and pickup. This is the green line on the curve. These are usually low current. Current is injected and the trip time is recorded. The results of all these tests are compared with the manufacturer's published trip curves to determine if the breaker is operating within the specified limits. Many manufacturers of primary injection test kits include most manufacturers' trip curves in the software. We'll examine the test set in more detail on the next illustration. The heart of the set consists of a microprocessor core unit. It is connected to a motherboard which contains a regulated power supply and some support circuitry. Software contained in the microprocessor performs the required real-time data collection, measurement, user interface, and output control functions. Let's take a look at the front panel of the control board to help familiarize us with some of the functions. 2 LED displays are noticeable right from the start. The one on the left is a time display. It indicates the elapsed time of the current pulse. The touch keys below set up the display readout. To the right is the current display. This displays the true RMS output current of the test set. It can also be put into memory mode to display prior readings. The touch keys below set up the range of the display. Here you'll find the initiate key to start the test. Below that is the stop button, and right below that is the pause button. A serial port is located here for connection to a computer. The lower control panel houses the input voltage display. Control power on and off illuminated buttons are here. The main power switch and ready indicating light are positioned here. Output power on light is right here. The output transformer supplies the bus on the test set, which can be set at 208, 240, and 480 volts, and is capable of generating currents up to 6,000 amps. The output power is available on the bus stabs located on the side of the test set. It is important to note that the test cables need to be sized for the proper current of the device being tested. This image shows a molded case breaker connected during a test. A video of this test will follow on the next visual. The set can also be used on insulated case breakers and low voltage power breakers. This video is courtesy of Travis Langer of Engineered Power Services. It shows a primary injecting testing of a GE 600 amp breaker. Awaiting testing are 800 and 1200 amp frame. Here you can see the breaker is clamped to the output bus of the test set, and the test is on the left-hand pole of the breaker. Current is incrementally increased on that pole, and you can see that the breaker eventually trips. It trips in 32.64 seconds after the current reaches 1,858 amp, a little more than 3 times the rating of the breaker. You can also see that a laptop computer is connected to tabulate the results. Secondary injection tests check the functionality of the trip circuitry. The process can be described as follows. The secondary injection test simulates the current and voltage transformer secondaries by injecting single-phase or three-phase currents and voltages into relays, devices into the secondary circuits, performing the corresponding checking and testing with normal and fault conditions. Circuit breaker manufacturers all have test kits available for use with their circuit breakers. These are known as the term functional test equipment. Here you see Eaton's Magnum DS breaker test kit and Square D's breaker test kit. These kits have a connector that plugs into a port on the breaker as seen here. The kits simulate overload shown in the blue line, short time delay shown as the red line, short circuits coded yellow, and ground faults displayed in green into the electronic circuitry to test the trip functionality of the breaker. Test set manufacturers also build secondary injection test kits to perform the same functionality. Here is a picture of a kit made by Megger and one made by SMC. These are all portable and designed for use in the field or a workbench. It might be a good idea to see a secondary injection test in action. This image shows a Square D Schneider Electric S33595 Full Function Circuit Breaker Test Kit, or FFTK. The kit has the functionality to automatically test for long time, short time, and instantaneous trip conditions. The kit automatically fills the values once the cable is connected to the trip unit. Each parameter is checked on a separate test. The following video shows the long time test only, but once the test is performed, the kit prompts you to proceed to the next parameter. It will do so until all three parameters are tested. This test is conducted on two breakers with two test kits. Both breakers passed the long time test. We continue our discussion on insulating materials to help us lead up to understanding insulation-resistant testing. Earlier, we looked at some considerations to account for when choosing insulating material. It is no accident that three of them are causes of insulation failure. They are electrical stress, mechanical stress, and thermal stress. There are two more other causes to be noted. Chemical stress can readily break down insulation. Environmental contamination also can have a damaging effect on insulating material. Electric motors are the heartbeat of industry. Let's examine the reasons why they fail. Here is a pie chart showing the causes. Let's look at how this breaks down. 25% of the motors fail because they are overloaded. 10% as a result of phase failure. 12% because of bearing failure. The balance, except for 5% of failures by other causes, involve insulation. 5% because of deteriorating insulation. The overwhelming 43% occur as a result of contamination. We can further break down the contamination failures with 17% from moisture, 20% from oil and grease, 1% from chemical, and 5% from chips and dust. That makes nearly half of all the failures resulting from compromised insulation. So you can see why insulation is so important. There are three basic types of insulation resistance tests. Short time readings usually are 60 seconds in duration. Time resistance tests, which include dielectric absorption, or DAR, or polarization index, or PI. Lastly, there are step voltage readings, which are mostly used for DC overpotential testing and can be used at insulation resistance test values. We'll spend more time on each of these. A short time readings test is the most common insulation resistance test. It is sometimes referred to as a spot reading. Let's look at this curve to understand what is being measured. The y-axis is megaohm. The x-axis is time. Notice the limitation of 60 seconds as the maximum time. To measure, simply connect the test device across the insulation and operate it for 60 seconds. The resulting value is then read and recorded. Some specimens will max out the meter after a few seconds. The test can be terminated once this occurs. Note that at 30 seconds the value will be less. Keep in mind that temperature and humidity, as well as the condition of the insulation, will affect your reading. Here are a few other important considerations. As a general rule of thumb, insulation resistance should be approximately 1 megaohm for each 1000 volts of operating voltage, with a minimum value of 1 megaohm. This is what is known as the 1 megaohm rule. For example, a motor rated 5000 volts should have a minimum insulation resistance of 5 megaohm. In practice, megaohm readings should be well above this minimum value when insulation is new or in good condition. By recording these measurements over time, you gain a better basis of judging the actual condition of the insulation. Any persistent downward trend is usually a warning that there's trouble ahead, even though the readings may be higher than the suggested minimum values. Periodic readings found to be lower than recommended values may be okay as long as they are consistent. Refer to the ANSI/NETA maintenance testing specification for recommended insulation resistance levels in the absence of manufacturer standards. Now let's look at some other insulation resistance tests. The first method is dielectric absorption ratio, or DAR. In this test, the testing device is applied and IR, or insulation resistance measurements, are taken after 30 seconds and 60 seconds. The test is independent of temperature and volume. The dielectric absorption ratio is calculated as DAR equals resistance at 60 seconds over the resistance at 30 seconds. The test can provide conclusive results as to the condition of the insulation. The test involves recording the 30-second reading first, then the 60-second reading. Then you can compare the resulting ratio to this table. Results between 1.0 and 1.25 are considered questionable. Ratios between 1.4 and 1.6 are considered good, and anything above 1.6 is considered excellent. The term Gill has been coined and named after Paul Gill, the author of the book entitled Electrical Maintenance and Testing, and used as a gauge to evaluate the condition of the insulation. A reading below 1.25 gills is cause for further investigation. The next time-resistant test method we'll examine is the polarization index. It represents the ratio resistance values of 10 minutes over 1 minute. Here is the formula. PI, or polarization index, is equal to IR, or insulation resistance at 10 minutes, over IR at 1 minute. It is based on the absorption effect of good insulation compared to that of moist or contaminated insulation. You simply take successive readings at specific times and note the differences in the reading. Tests by this method are sometimes referred to as absorption tests. Note that good insulation shows a continual increase in resistance as seen in curve A over a period of time in an order of 5 to 10 minutes. This is caused by the absorption current we spoke of earlier. Good insulation shows this charge effect over a time period much longer than the time required to change the capacitance of the insulation. If the insulation contains much moisture or contaminants, the absorption effect is masked by a high leakage current, which stays at a fairly constant value, keeping the resistance reading low as you see in curve B. As we did with the DAR numbers, we can compare the polarization invoice numbers the same way. A value of less than 1 is considered dangerous. A value of 1 to 2 is questionable and should lead to further investigation. A value of 2 to 4 is good, while values above 4 are considered excellent. The step voltage test uses different voltage settings during the resistance testing. In this test, each test voltage is applied for the same length of time, usually 60 seconds. Each test is then recorded and placed on a graph in order to compare the values as seen in this example. By applying increasing voltages in steps, the insulation is exposed to increased electrical stress that can reveal information about compromises in the insulation, such as pinholes, physical damage, or brittleness. Good insulation should withstand an increase in overvoltage stress, and its resistance should remain approximately the same during the testing with the different voltage level. On the other hand, especially at higher voltage levels, deteriorated, cracked, or contaminated insulation will experience an increased current flow, resulting in a decrease in the insulation resistance. This test is independent of insulation material, equipment capacitance, and temperature. It is advisable that this test be performed only after an insulation spot test has been inconclusive. A spot test deals with absolute resistance change in a single reading with respect to time, while the step voltage test looks for trends in resistance with respect to variant test voltages. In this example, we have chosen 3 voltage steps. At 250 volts, you will notice the resistance increases. As we step up the voltage, we would expect the resistance to decrease as we see at 500 volts, and the sharpest decrease occurs at 1000 volts. Next up, we'll touch on how to make connections to the test set for insulation resistance testing. First, let's review the specimen. In this case, it's an electrical cable. It is made up of an external casing or insulation. Next, you see the shield or braid. Next is an internal layer of insulation. Then finally, the conductor itself. In our example, we will be using an AEMC 5050 megaohm meter as seen here. If we zoom in, we can see the test set terminal. First is the positive terminal marked on the set by a red and white plus sign. Next, you'll find a guard terminal designated by a blue and white G. The guard terminal is used to divert surface leakage from the measuring circuit. Not all insulation testers, such as handheld megaohm meters with outputs of 1000 volts or less, are equipped with a guard terminal. The last terminal we will use in this test is the minus connector, designated by the white minus symbol. Okay, now let's go over the connections to the specimen. The shield or braid gets connected to the earth plus terminal on the set. The insulator gets connected to the guard terminal, and lastly the conductor gets connected to the line terminal labeled minus. Insulation resistance testing is not only limited to wire and cable. Electric motors and transformers can fail if there is a breakdown of insulation. Here are the connections for testing insulation in transformers using the AEMC 5050 test set. With the power removed from the transformer, primary terminals H1, H2, and H3 are wired in series and terminated at the minus terminal on the test set. Next, the secondary terminals X1, X2, X3, and X0 are wired in series and then connected to the guard terminal on the test set. The enclosure should be clamped and connected to the plus terminal. It is also important that the transformer be firmly grounded. Now the transformer is ready for testing. Now that we know the test lead connections, we can further get the test set ready. First, we select what type of test we desire. This can be accomplished by toggling the R-DR-PI-DD button. By toggling through, you can select R for resistance, DAR for dielectric absorption ratio, PI for polarization index, and DD for dielectric discharge. These abbreviations are shown on the display screen as you toggle through them. Next, the duration of the test can be set by selecting V/time button. The voltage selector switch can be rotated to fix the test voltage value. After the selections are made, the Start/Stop button may be pushed to start and stop the test. Caution is needed before, during, and after testing. These pointers should be present in every technician's mind. Because the insulation resistance tester produces significant DC voltages, it should never be connected to an energized circuit. For this reason, some testers are equipped with voltage sensing capabilities that will warn technicians when voltage is present on a circuit. It is also a good idea to follow lockout-tagout procedures. The output of an insulation tester can destroy electronic circuits, which is why they should never be connected to electronic power supplies, PLCs, variable speed drives, UPS systems, battery chargers, or other solid-state devices. Insulation can hold a significant charge for a period of time after the insulation resistance test is complete. Long cable runs can store a considerable amount of energy when testing is complete. Some testers have an automatic discharge feature that will discharge the insulation after testing. Others do not. Most technicians will ground the circuit under test after the test is complete to verify the insulation is discharged. Some manufacturers recommend the insulation resistance tester remain connected to the circuit or component under test after the test is complete for up to 4 times as long as the test was conducted to ensure a safe discharge. One final note on insulation resistance testing. Megger has published an excellent manual to guide a technician through resistance testing. It is entitled A Stitch in Time, The Complete Guide to Electrical Insulation Testing. It covers insulation basics, how to interpret readings, temperature and humidity effects, as well as connection methods to a variety of equipment. To get a copy, go to the Megger website or search the web for the title. A watch pot never boils. I was told this numerous times by my parents as a youngster. Well, the same can be said in our industry. Equipment will not malfunction while watching it operate. Many a technician has been called out because maintenance has experienced an abnormality. Hours can be spent waiting for it to occur again, and it does not occur. But within 10 minutes of leaving the building, your cell phone rings asking you to return. A recording instrument like this Fluke 289 True RMS data logging multimeter can help. Once it is set up, it can log any number of parameters and capture abnormal conditions. The values can be reviewed at any time. In many cases, it can pinpoint the cause for nuisance performance of electrical equipment. Microprocessor protective relays do a great job of capturing similar data. In the absence of this protection, recording multimeters can speed up the troubleshooting of electrical equipment. Vacuum interrupters have been in use since the 1980s to replace air contacts in circuit breakers and low voltage and medium voltage contactor. Many of these components are still in service today. Conventional testing on these devices include a high-pot test to examine the dielectric strength of the device and a contact resistance test to determine the health of the contacts. We reviewed these tests previously in this lesson. Although these tests provide good information, they are basically go or no-go tests. They cannot determine if and when the vacuum interrupter would fail. That is where the so-called MAC test comes in. MAC stands for magnetron atmospheric condition. This test is a predictive test that can provide information of the remaining useful life of the vacuum interrupter. Let's spend some more time examining this testing method. Here are some of the test set options that are available. Lab bench models have been and still are in use. This limits the technician to the size of the interrupter that can be tested. Portable testers like Vacuum Interrupters TS4 seen here provides more mobility. It can be set up in the field to test various sizes of interrupters. Other test kits available are the HVI High Voltage PFT 301 CM High Pot Vacuum Bottle Tester, Phoenix Tech Model 640-0.4 Portable 40 kV Vacuum Interrupter Test Kit, and Megger's VI-DAR Test Kit. In order to properly understand how MAC testing is applied to vacuum interrupters, it is important to first review some principles and theory. The high interrupting capacity of a vacuum interrupter is based on the physical principle discovered by Louis Paschen, which states that the dielectric strength of a gas is a function of the gas pressure, the distance between the two electrodes, and the type of gas. The result of this function is the vacuum interrupter breakdown voltage. The dielectric strength remains constant until the pressure starts to decrease, which will result in a failure of the vacuum interrupter. How does the vacuum technology work? The bottle consists of two primary contacts enclosed in a vacuum-type envelope made of ceramic material. Each end is sealed with a metal end cap and end shield. Inside the envelope are two contacts, sometimes called electrodes, one fixed and one movable. The movable electrode travels through a bellows connection which is covered by a shield. When the contacts are separated, the arc is supported by ionized vapor derived from the contacts themselves rather than by ionized gas. Although the physics are complex, the interrupter works because the arc does not have a conducting path and cannot be sustained in a vacuum. New spiral-shaped contacts provide a self-induced magnetic effect that moves the arc around in a circular fashion, which minimizes the contact erosion. The MAC vacuum interrupter leak test is based on studies by Franz Michael Penning, and his discovery is called the Penning discharge principle. The principle showed that when a high voltage is applied to open contacts in a gas and the contact structure is surrounded by a magnetic field, the amount of current flow between the plates is a function of the gas pressure, the applied voltage, and the magnetic field strength. Charged particles or ions can be generated from high voltage supplied across an open vacuum interrupter. When a strong magnetic field is applied to the vacuum interrupter, these ions will move, which produces a current across the open contacts. The magnetic field can be a flexible magnetic field coil used without removing the breaker element seen here, or a magnetic coil fixture when the vacuum interrupter can be removed from the breaker as shown here. Various sizes are available depending on the vacuum interrupter. The ionization current that is produced is directly proportional to the pressure inside the vacuum interrupter. By comparing this value with a known pressure ionization current curve, the pressure inside a vacuum interrupter can be easily determined through the Penning discharge principle. By using this comparison, it is possible to predict the approximate remaining life of the vacuum interrupter. This allows for a scheduled change out prior to a catastrophic failure. After spending time discussing the theory of MAC testing, let's familiarize ourselves with the test equipment itself. We will go over the features of vacuum interrupters MAC TS4 as seen here. The test set has a backlit LCD screen. It also houses a 2.2-inch thermal printer. A USB port is provided to connect to a computer. There is a selector knob that interfaces with the LCD screen and allows for setting up the test parameters. The on-off power switch is seen here. Right next to it are 3 protective fuses. The high voltage input is here. Flexible and fixed magnetic field inputs are here. The signal input gets connected here. A ground terminal is also provided. The set includes a power cord, a high voltage output cable, 2 magnetic coil output cables, one to be used with the supplied flexible magnetic field coil, and a second that can be used with a fixed magnetic field coil. It also includes a signal input cable, ground cable, USB interface cable, and Windows-based software. Here is an example of a flexible magnetic field connected to a breaker in the field. The unit is portable and can be set up easily for field testing. This image shows the connection to a fixed magnetic field. Note the red output cable connecting to the top of the VI. The magnetic field coil connects here and the signal cable connects here. The flexible magnetic field coil connections are very similar except that the magnetic coil output cable connects directly to the VI. More informational data and videos are available on the Vacuum Interrupters website. For all the quiz questions, click on your answer, then click on Submit. Then follow the on-screen instructions. Give some time for your answer to record. Note that only clicking on the Submit button will record your answer. Here are your quiz results. Please note your score and record it. If the score is below the passing grade, you may retake the course and complete the quiz questions. If you receive the passing grade, please note the score and click on the next prompt at the top of your screen to complete the form for your certificate.